Hey guys, we'll go over the answers for the homework, but first we'll have your daily objective. So I'll put a little time up for you to get organized, and then we'll get started. So hopefully you guys got all these. Normally I would just put up the answers and see who has questions, but since I'm not here to answer questions, I'm just going to go through them. There's not that many of them though, so hopefully this won't take terribly long. So number one says, what is the energy of a light wave with a frequency of 4.67 e to the 18th hertz? So this is a pretty simple one. Our equation tells us the energy is equal to the frequency multiplied by Planck's constant. So in this case, all we do is take that number and multiply it by Planck's constant. So 4.67 e to the 18th, multiply it by Planck's constant, which I have saved in my calculator, and we get 3.0, well actually, rounded to three significant figures, it would be 3.10 e to the negative 15 joules. Okay, number two says, what is the frequency of an electromagnetic wave with an energy of 10 joules? So, okay, basically the same equation, except now we know that the energy is 10. We don't know what the frequency is, so we're going to have to divide. Actually, probably make more sense. Do it the other way. Divide 10 by Planck's constant. So 10 divided by Planck's constant, we get a frequency of 1.51 e 34th hertz. Okay, those two hopefully were fairly simple division or multiplication. Now number three is a little bit more complex. It says how much energy is carried by an EM wave with a wavelength of 400 nanometers. So here we can't just do the one equation, because energy equals frequency multiplied by Planck's constant. We need to know what the frequency is. So first we're going to have to use the other equation, the speed of light equation, to find the frequency based on the wavelength. But even before we do that, we've got to convert this thing, because 400 nanometers is not something we can put into this equation. We need our wavelength in meters. So we're going to convert from nanometers to meters, and we should get 4 e to the negative 7th meters. We can then put that in here with the speed of light. So we'll divide the speed of light by 4 e to the negative 7th. We get a frequency then of 7.5 e to the 14th hertz. And now we can take that and multiply by Planck's constant to find an actual energy. So when we multiply by Planck's constant, we end up with 4.97 e to the negative 19th joules. Okay, now going through this, I don't have you guys to check me and tell me if I made a wrong mistake, so feel free to pause this if everybody else has the wrong answer, and you can take a look at it and see if I screwed something up. But these are fairly simple ones. I don't think I'll make too many mistakes here, unless I hit something wrong in the calculator and don't notice it. Okay, number four, what is the energy of a light wave with a frequency of 11.3 hertz? So this one's pretty simple. multiply 11.3 times Planck's constant. And we get 7.49 e to the negative 33 joules. Not much energy in a wave that's long enough that it's only got a frequency of 11.3 hertz. Number 5, what is the frequency of an EM wave with an energy of 5.62 times 10 to the negative 12? This one again, we only have to use the one equation. So we divide that energy by Planck's constant, and we get a frequency of 8.48 e to the 21st hertz. Okay, so again, those last two, fairly simple, one equation. But number 6, here's where we have to go through a couple steps again. We need to know energy. Our equation for energy uses frequency, but we're given a wavelength, so first we have to convert. Luckily here we don't have a unit conversion to do. It's already in meters. So speed of light has to be equal 50 times the frequency. So we'll just take the speed of light divided by 50, and we get 6 e to the 6th hertz. We can then put that into the equation by multiplying by Planck's constant. We get 3.98 negative 27 joules. Number 7 is a little bit more interesting of a problem. It says the energy gap between the first and second energy levels is a certain number of joules. If an electron falls from the second to the first energy level, what kind of light will be given off? So we know the energy is 1.68 e to the negative 17th joules. That has to be equal to our frequency times Planck's constant. So in this case, we'll divide by Planck's constant. And that gives us a frequency of 2.53 e to the 16th hertz. Now from that, you might be able to look on your spectrum and see what kind of a wave that'll be. I think about it a little bit easier in wavelength, so I'm going to go ahead and convert that to a wavelength using the speed of light equation. So I'll take the speed of light and divide it by that frequency, and that gives me a wavelength of 1.18 e to the negative 8 meters, or about 11 nanometers. And it turns out when we look at our spectrum that this is going to fall in the UV range. And that's pretty general. In a lot of atoms, if we have electrons falling all the way to the first energy level, it's going to give off some sort of UV light. Okay, next I have a worksheet for you to use to practice some more molar mass problems. Based on the last test, I think some people need some review on that. So again, these problems are going to be important later on down the line. So I got a few problems on this worksheet. Really 10 minutes should be enough to cover it. I'll give you 12 though. So do those problems and then we'll go over them. So you've had some time to look at these review problems on molar mass. So let's go ahead and go through the answers for those. Number 1 says, what is the mass of 17 moles of nitrogen atoms? So I've got 17 moles. I need to know the mass. Anytime I'm thinking about mass, I should be looking on the periodic table. My molar mass for nitrogen is about 14.01 grams for every 1 mole. So I put moles on the bottom so they'll cancel out. I'm pretty much done. You just need to multiply 14.01 times the number of moles. And we get 238 grams, rounded to 3 significant figures.
Number 2 is the same basic setup. We've got the number of moles. We need to convert that to grams. The only difference here is we're talking about lead now instead of nitrogen. So for lead, our molar mass is 207.2 grams per 1 mole. But we're still doing the same basic math. We take the number of moles, 0.256, multiplied by the molar mass of 207.2. and we end up with 53.0 grams.
For number 3, we have to be a little bit careful. It says, how many moles of atoms? Now we're talking about moles of atoms. Remember, a mole is a way of kind of taking that number and turning it into a little bit easier terms. So we're not finding the number of atoms. Okay, we can just talk about how many moles here. That might be a little bit simpler, but don't get confused about that. Anytime it says moles of something, we're finding moles. So we've got 2.63 grams. And we need to figure out how many moles that is. Well, we have to divide by grams to get that off the bottom. We're going to convert that to moles. But again, anytime we're talking about mass here, we should be thinking about the periodic table. So if we look on the periodic table, the molar mass of fluorine is 19 grams for every 1 mole. So we take 2.63 divided by 19, and we get 0.138 moles. That should make sense. We need 19 grams to make a single mole. We're not going to have a whole mole here because we only have 2.63 grams. Okay, number 4, same basic type of problem. 17.3 grams, except now we're talking about zinc. We still have grams on the top, moles on the bottom. But zinc's atomic mass, there's molar mass, I should say, is 65.38. Oops. Now I went and put that in the wrong spot. Let's back that up. Because it's not 65.38 moles per gram, it's 65.38 grams for every 1 mole. But in this case, we do the same thing. We take 17.3 grams, divide it by the molar mass. In this case, it's 65.38. And we get 0.264 moles. Okay, this is moles of fluorine. This is moles of zinc. This is just preference. I would not take off if you didn't put of fluorine or of zinc. I mean, it's obvious that's what we're talking about because that's the only element that's there. So that's some review on molar mass problems. Remember this test, even though we're not really talking about molar mass, we still will have at least 1, if not 2 problems on there because this stuff is important enough that we got to review it time and time again. Okay, that's all I've got. I don't have any homework for you for Monday, but Monday we will review, and then Tuesday we're going to have a test over this stuff.